Here we're going to talk about arc length. So we're going to find the length of this curve. Okay, so finding the length of a curve, integral or A to B. So we've got this curve. Ooh, I wrote A to A, so A to B, sorry. And I want to find the length of that curve. Now, to do this, we start with an approximation, just like we do in everything else in calculus. So we start by approximate. So we can approximate little line segments Okay, what do I mean by that? Well, say I broke this line up into little segments here. So, and then I found the distance between 2 points, which I know how to find that distance. And I find the distance between all these points here. That's a way to approximate how long the black line is with the points. It's an approximation. It's not exactly accurate, but the more little line segments I have, the better. The approximation becomes better and better the more little line segments I get. So, for example, say instead of having that, maybe I break it up and have it like this. Okay. So now I've got several more line segments, and I find the lengths of all those little line segments. Now all of a sudden I've got a pretty good estimate of how long that curve is. So let's take one little piece here and zoom in. Okay, so let's zoom in and see if we can't figure out what's going on here, how we're going to write this into calculus. Okay, so let's zoom in. So when I zoom in on my little black curve here, okay, so I had a dot here and a dot there, and the approximation was this distance between the dots, even though we're trying to figure out what this length is right here, okay? So how do I represent that? Well, this is more of the hand wavy part here. So let's call this triangle. Let's call this side the change in y, and let's call this the change in x, if we're talking about a curve on the x and y axis. So how far this changes from here is the delta x, okay, and then the delta y, that's how far we go from here down, right? Okay, so and this is a right triangle. What do we know about right triangles? Well, the Pythagorean theorem what does the Pythagorean theorem say? It says a squared plus b squared equals c squared, right? Well, we don't want to know what c squared is. We want to know what c is equal to. So I take the square root of both sides to get c. Okay. So what is this really? So c here for this triangle is equal to the square root of delta y squared plus delta x squared. Okay? And so what I'm going to do is I'm going to factor out a delta x squared out of that inside there. And so if I factor that out, I have delta x squared factored out. And then if I pull a delta x squared out of this, I have delta y squared divided by delta x squared, okay? And then plus 1, all right? So just to make sure that this works, if I multiply this back in here, I get just delta y squared. If I multiply this in here, I get the delta x squared. Okay, so we're good. Now what am I going to do? Well, I have this product times this product here. Since we're dealing with positive distances here, each of these components are going to be positive. So it is the square root of delta x squared times the square root of, well, I can combine both of those are squared, right? So I'm going to combine this to be delta y over delta x all squared plus 1. All right, and so what do I have here? Well, the square root of the square is actually equal to the absolute value of the delta x. But what do we know about the delta x? It's positive. Okay, that change in x is positive, so I can drop the absolute values. So it's delta x times what? Well, what is delta y over delta x? Delta y over delta x happens to be the derivative. So this is the derivative of the function if y is equal to a function of x, right? So f prime of the derivative plus 1, okay? And the derivative is squared. And my delta x here, all right, that's kind of like, that's my differential there. So that's one little segment here is represented by this one here, okay? And so, and once again, this is hand waving going on here. I'll show you the mathematical proof for those interested in just a second. But for our purposes, we see to sum one of those little things is this formula here. But what I want to do is I want to sum all of them from A to B. Well, how do I sum infinitely many little line segments from A to B? Well, there's one way I know how to do that, and that's with an integral. Infinite sum A to B, okay, of what? The square root of 1 plus the derivative squared dx. Okay? And so this is equal to the arc length. So the arc length, if you didn't get anything else, write this down. This is the formula for arc length, okay? So this is how we find arc length, provided f prime is continuous on A to B. Okay, provided f prime is continuous on A to B. Now this derivative, you'll note you're taking the derivative with respect to x. So this is dy dx. It's with respect to x, right? So I want you to make sure you understand that, even that differential with respect to x there. Okay? So very important that you understand that. Now, if it was a curve like this, maybe it's find the distance. So maybe this is like y equals x squared plus 1. And I want to find the distance between 1 and 2 on the curve. So what I'm looking for is that distance between here and here on the curve. How long is that measurement there? So how would I do this? So my f of x is equal to x squared plus 1, right? So I'm integrating with respect to x. So I sum all the segments from 1 to 2, right? So the integral from 1 to 2 of the square root of 1 plus, now the derivative squared. So I need to find the derivative here. The derivative f prime of x is 2x, okay? So the derivative squared dx. And so this is equal to the integral from 1 to 2 of the square root of 1 plus 4x squared dx. All right, so what I'm really looking for, I'm looking for you to be able to set up this integral here. Now, up to this point in calculus, all we have for tools, oh wait, no, yeah, we do. We've got the tools to solve this. So, but when we do this section, okay, I'm fine with you using your calculator to get this answer for this one here. Okay, if you think you can solve it by hand, go for it. Okay, I'm not going to stop you at all. All right, but there's a way to do this in your calculator. So if you got a TI 84 plus, okay, TI 84 plus, you hit the math button. And then you hit the 9 button. The 9 button is FN int, which means integrate the integral, the function, integrate the function. And then what do? Well, it's a parentheses. The first thing you put in is the function, okay? Whatever variable that you use. For this one, it's x. And then the next thing that you do is the variable. Okay, the differential, we differentiate with respect to x here. Okay. The next thing that you do after that, and remember you're putting commas in between each one of these things. So the next thing after that is the lower limit. Okay. And the last thing in general is the upper limit. So you're putting commas between each of these. And then you close it off right there. So for this particular one, the function is the square root of 1 plus x, 4x squared. So I'm going to plug in square root 1 plus 4x squared. And then the variable, what's the variable that we use? Well, I use the x, okay? And then the last two things, well, the lower limit, that's 1. The upper limit is 2. So in your calculator, you do math 9, and then it'll have this FN int, and then a parentheses, and you type in the square root button, okay? So the squirt button, 1 plus 4x squared, comma, x, comma, 1, comma, 2, close parentheses. And if you do it right, let's see, what will you get? Let's see, I'm not even sure I can do this on this cheapo calculator. By cheap, I mean free, right? So let's see if you can even do this. Math, and then I go to 9, enter. Ooh, okay, mine sets it up beautifully, so I don't even have to type all that in, right? So I'm going to do, what was the problem? It was from 1 to 2 of the square root of 1 plus 4x squared, okay, dx, right? I think that was what it was. Okay, yes. Now I'm going to hit enter, and I get 3.1678. So 3 decimals, 3.168. All right, so that would be what I would expect to see here. I want to see you set it up like this, and then write out the simplified. If there is, I mean, there's not much, you just square it, right? And then you can say, okay, this is equal to 3.168. All right. Trig substitution here, I guess you could do, I don't even know. We could try trig substitution, see if that works. 1 to 2, square root 1 plus 4x squared dx. If I tried trig substitution, let's just see if it works. Who knows? Okay, square root and then plus in the middle. So I'm going to say 1 leg here and 1 leg here. So that means this is, hypotenuse is 1 plus 4x squared. Okay, so that's my angle theta. So cosine, so secant theta is equal to square root 1 plus 4x squared. I need to get a differential, so tangent theta equals 2x. So 1 over 2 gets me x. So dx is equal to 1 over 2 secant squared theta d theta. Yuck. This is going to be integrate 1/2 secant cubed theta d theta, which you and I both know that that's one of those tricky ones, right? So you can run through this, and you're actually going to have to use integration by parts. Split it up to secant theta times secant squared theta. I'm not asking you to do that. If I tell you to use a calculator to get final answer or approximate answer, whatever, then that gives you the license to go from right here to right here, okay? If I don't tell you what to do there and I just say solve it, then I am asking you to integrate secant cubed, which I'm not, that's a tough one. I think I did a video where you integrate secant cubed, okay? So hopefully this helps you understand the formula. Let's do, I want to do, yeah, okay, we can write it out in terms of y, because that was with respect to x. Sometimes the function, if a curve is x as a function of y, okay, x as a function of y, right? So this is like x equals g of y for some y value between c and d, okay? And what else do I know? G prime of y is continuous. If this is the case, then the arc length L is equal to the integral from c to d of the square root of 1 plus g prime of y squared dy, where once again we take the derivative with respect to y. Okay, take the derivative with respect to y. So it's d dy g of y equals g prime of y. Okay, I'm taking the derivative of g with respect to y. Okay, and then I square it. So like say you had this problem here where your curve is like this. Okay, and this is x equals y squared curve. So this is x as a function of y, x as a function of y here, and maybe I want to know how far it is from here to here, okay? So maybe it's like from y equal to 2 down to y equal to -1. So to integrate this, to find that arc length there, that arc length would be equal to the integral from -1 to 2 of what? The square root of 1 plus the derivative squared. Well, what is the derivative with respect to y? So d dy of x equals d dy of y squared, which is 2y. Okay, so I plug in 2y here. For my derivative, I square it, and then I integrate with respect to y. Okay? So, simplify that a little bit. -1 to 2, square root 1 plus 4y squared dy. If I integrated this in my calculator, so do the integral here, math 9, enter, -1 to 2, square root 1 plus 4, 4y squared, and I wonder if I can delete the dx. Okay, so mine doesn't let me do that, but if you wanted to, you use that y as a dummy variable, you could just use x again. So what I'm trying to tell you is when you type this into your calculator, instead of using y in your calculator, you can just do the fn int. If you're more comfortable using x's, that's fine. Just be consistent. 1 plus 4x squared, comma, x. Whatever letter you use here in your 84, use it there, right there. I can't show you because I don't have it on my iPad. It only uses that free software. And then from -1 lower bound to upper bound 2. Okay? And so type that in and you'll get something, right? So let me just redo this again. I wonder if I can, let's change, oh man. Okay, let's do, what did we say, -1? Okay, so let me see if that's right. So yeah, -1 to 2. So 6.126. All right, so just like that. No biggie there. Okay, so that's how you use the formula to get the arc length. Let me show you, for those that are interested, let me show you the proof behind why this is true. Okay, so let's go back to our picture. I'm going to use this picture to help me out here. Okay, so let's just say that this is some arbitrary, so I have my line here, and I have all of these random segments, infinitely many, but then let's just say that there's some arbitrary xk value. It's a partition. We're going to partition up. So I have my x1, x2, x3, dot, 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 xk, xk plus 1, dot, 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 xn minus 1, xn, right? So xn was A or B, and then x1 is A. So you got your starting point and your ending point there. All right? So to get this middle segment here, once we get that arbitrary segment, then we got it figured out. So you got your xk and your xk plus 1, but whenever I plug it in up here, it becomes f of xk and f of xk plus 1. Okay? So this point is xk, comma, f of xk, and this point down here is xk plus 1, comma, f of xk plus 1, right there. Okay? Now, I'm going to call this L1, L2, and then so on all the way to LK here. So this LK, that's the length of that line segment there. I'm just giving these pieces names. How do I find the distance? If I draw my triangle there, right? How do I find the distance from here to here? Well, that distance is this distance between xk and xk plus 1. So this distance is equal to xk plus 1 minus xk. Okay? And then how do I find the distance from here to here? Well, that's this top piece minus that bottom piece, right? So it's f of xk minus, I'm sorry, it's right minus left. So when you're doing that horizontal, sorry about that. That's f of xk plus 1 minus f of xk. Okay? So remember we're going down this way. That slope, that's a negative slope going on there. Okay, so that's my change in y, and this is my change in x. So what do I know? Well, by the mean value theorem, what do we have? We know there exists some ck value that's between xk plus 1 and xk. So there's some value between these two values. There's some ck value such that whenever I plug in ck, it has the same slope as this lk line. Would it make sense that there's some ck value that whenever I plug it in, it has that same slope, all right? So meaning the derivative evaluated at ck is equal to this same slope that's right here, rise over run, right there, which is f of xk plus 1 minus f of xk over xk plus 1 minus xk, right? So by the mean value theorem, this is guaranteed, okay? Now what do I know about this piece right here? Well, remember this piece right here is delta x, okay? So I'm going to multiply both sides by delta x. And so those cancel. So I get f prime ck delta x equals f ck plus 1 minus f ck plus 2. I'm sorry, xk. I'm sorry, that's what that is right there. Sorry, said that wrong. All right, so now what am I doing here? What am I trying to do? Well, if I use Pythagorean theorem on this triangle here, I have a squared plus b squared equals c squared. So what does that mean? That means f of xk plus 1 minus f of xk squared plus delta x squared equals lk squared. All right. Now I don't want the length squared, so what do? I square root both sides, and so I find that lk is equal to the square root of what? Well, it's this piece right here. What do we know about this piece right here? Well, it's this piece right here, except for I need to do what? I need to square it. But if I square this side, I got to square this side. So I can replace this with this. So this is f prime ck delta x squared plus delta x squared. All right. So now what I can do is factor a delta x squared out of both of these. So as f prime ck squared times delta x squared, right? Plus delta x squared. If I factor out a delta x squared out of here and here, what do I have left? Well, that gets me the derivative squared plus 1 times delta x squared, okay? And then what do I know? The square root of the square is equal to the original thing, right? So this is equal to the square root of the derivative squared plus 1 delta x, okay? And so I've just proven that one LK arbitrary length here is by definition this piece here. So if I integrate all of these arbitrary lengths here from A to B, that's where I get the arc length A to B. So L is equal to, actually, let me rewrite this. So L, the real arc length, is equal to the limit as n goes to infinity of the sum from k equal 1 to n of the LKs. So this is a fancy way to say the limit as n goes to infinity of L1 plus L2 plus L3 plus all the way out to Ln. If I limit that to infinity, I get the real arc length. And so if I have n little line segments, but that n is going to infinity, this set number of n turns into infinitely many little line segments, infinitesimally small. Okay? So that tells us that the formula is equal to a to b square root 1 plus the derivative squared dx. All right? As long as the derivative's continuous on a to b with respect to x.